the tail end of Application Insecurity. So through today, we'll learn about modern exploitation techniques and also modern, we'll learn about modern defenses and modern exploitation techniques. Yes?
Is there any more homework assignments or just the project left?
We'll see. What would you rather have?
Project only.
Why?
So I can cry less.
We'll see. Gotta be a little bit flexible with this thing. Depends on how fast we cover things, how much other stuff there is. Don't worry about it. Okay, so we looked at all types of memory corruption attacks, right? We've seen, so fundamentally, what do we mean when we talk about memory corruption? What's the root? What can an attacker do on the system or on our process? Yeah. Huh? Yeah, that's one of the, that's a type of memory corruption. What is a memory corruption? What does it mean? Yeah.
What is the goal of it? Is that what you're asking?
Yeah.
To change the save IPs when the function returns, it calls whatever code you want.
All right, more broadly, right? Memory corruption means that we can write, the attacker can write to memory that they shouldn't. Very broadly, right? What they want to do is that depends on their goals, right? They can change EIP, they can do all kinds of stuff. So, there's been a lot of research over the years on how can we actually prevent these memory corruption vulnerabilities. Why is this so difficult? What makes this difficult?
You need to write to memory at some point.
We need to write to memory, right? The program needs to write to memory. It stores its values in memory, the variables in memory, right? And fundamentally, it's difficult to know, hey, is this write to memory good because the programmer intended it to happen, or is it malicious because an attacker is tricking the program to do that, right? And furthermore, it may even be the fact that you can write to a certain location, but if you're able to write a certain value to a location, that's what causes the vulnerability, right? So fundamentally, even though on the surface it may seem like buffer overflows are kind of easy to prevent or think about, right? You just check the bounds of a buffer before you write to it. Generally, memory corruption is incredibly difficult, and that's why there still are many buffer overflow type vulnerabilities and memory corruption vulnerabilities today. So the best way to prevent this is to just write programs that don't have these vulnerabilities, right? Have you ever written a non-buggy program in your life? What was that? Hello World? Even I messed that up. I'll tell you, it literally wasn't, it must have been, I think it was my first or second year here. So when I've been programming for, I don't know, I'm not calculating, a long time at that point, that I wrote like a 20-line Python script and it actually worked for the first time without any bugs. Like I was shocked. I actually spent more time looking at the code because I didn't understand that and I didn't believe that it was actually correct. So think about doing that for 20 lines. Any sufficiently complicated program is going to be basically essentially impossible to write correctly. Right? So another way is just say, hey, never use C or C++. Use some other language that completely eliminates this entire class of vulnerabilities. So what do you think? Is this good advice? Is this how we can prevent these?
Depends on the platform.
Depends on the platform? You want to elaborate?
Well, like if you need the benefits of C, or like if you're programming on Linux, I guess, if you need like the performance, then you can go for C. But if you don't, then maybe it's safer to use Java.
So it could be for performance reasons that we choose one over the other. Let me check and make sure. I didn't actually check to make sure that the. I'm gonna check. Okay. So yeah, we can do this if we want slow programs in general, right? Does that mean we've completely eliminated the problem? We move on to Java or Python or Ruby, Haskell. Yeah.
What if the interpreters have bugs that allow buffer?
So what's the JVM written in? C or C++, I don't actually know. But one of the two, right? And so what if there's now a memory corruption vulnerability in the JVM itself? Is that a good trade-off, bad trade-off, what do you think?
Most likely to have it in the JVM than it is in your code.
Yeah, it's a little bit, you're passing the buck to the JVM, right? And so, well, you can say that, hey, just like it's hard to worry too much about bugs in the operating system. There always will be some, but you can only control your application code that you can control, right? But I think the counterpoint to this is when you look at browsers, right? Browsers essentially execute JavaScript, right? By design, there's no memory corruption vulnerabilities in JavaScript, but JavaScript programs run in browsers and are interpreted by JavaScript engines, which are written in C++ for performance reasons. And they very frequently, like, I don't know a stat, but I'd say at least once a month would probably be a good baseline. There are vulnerabilities that allow JavaScript executing in your browser to execute arbitrary code on your system, right? So, and this has been for years this way. So another aspect we can do is say, hey, let's try to find the vulnerabilities before they occur, right? So let's statically analyze the code to try to identify all the vulnerabilities before we execute it. So this is actually a huge area of research, and it's part of, I don't work yet on binaries, but this is essentially what part of my research tries to do is automatically find bugs and vulnerabilities in a program. The problem is that, have you heard of the halting problem? Can somebody restate the halting problem? Go somebody else.
I really can't say for sure whether or not it's actually going to complete because it's never like,
What?
you can't say whether or not you're going to find all the bugs in it. It's like,
What is a halting problem in general? So what does the halting problem say?
I think it says that you can't ever determine whether or not a program will finish or terminate or not correctly.
Yes, but I'm rephrasing it slightly to say I may be able to tell, but you can't write a program that's able to tell if another program will terminate or not on all possible inputs, right? It turns out you can reduce this problem of finding every single security vulnerability in a program. You can reduce that to the halting problem. And so fundamentally, we cannot write a program that can find all security vulnerabilities in another program. It's fundamentally impossible. So that's actually where, if it was easy, then it would be a fun research area, right? So it's very difficult to actually do this. And so it's all about making trade-offs about, you're always going to make mistakes in one direction. Either you say there's a vulnerability when there isn't one, or you'll miss a vulnerability. Those are your two choices. Question?
So does the halting problem fundamentally tell us that you cannot ultimately 100% secure any system?
I don't know that the halting problem says that. It's more, I would say, the halting problem basically says you can't write a program to verify another program, right? I think you can, something that's fundamentally secure is also very difficult to say conclusively, right? So, we'll leave that. The other ways to prevent is make exploitation harder, right? So the idea is by raising the bar and making it more difficult to exploit, and we'll see what we mean by more difficult here, we can maybe prevent kind of your run-of-the-mill attackers, right? We may still have those adversary state-level funded attackers that can still exploit stuff. The other way to think about this is detect it, right? So prevention means, hey, let's stop it from ever happening. So can we ever get 100% prevention? No, there's always going to be some problem. So we also need detection because we need to know when something bad happens, right? So for detection, we can try to perform checks on the program during execution. So as it's executing, you can have it try to examine its environment. We can try to analyze the system calls that it's making, essentially build a profile for each application and see when it's executing weird system calls. You can detect write and execute action sequences. So this is really popular in Windows malware, is to write out to a file and then execute that file. We can do integrity checking, so we can, during runtime, check maybe the EIP to make sure that EIP hasn't been tampered with before we return. So, we're going to look at making exploitation more difficult because this is a lot of technical areas here. And so we're going to go kind of semi-historical of how things were developed. So the very first thing people thought of was, hey, part of what makes exploitation really easy is the stack is executable, right? So you can jump to code on the stack and it'll start executing. Should a normal program ever need to execute something on the stack? What would need to? Let's flip that around. Is it true that all programs don't need to execute code on the stack?
No.
Why not? What's an
Something
example?
like an interpreter might need to start executing some code on the stack, potentially, depending on how you
Close.
write it.
Close. Interpreter is not quite the right word. What was that? So an interpreter is interpreting the text and doing its own code execution depending on the program. And a compiler is going to generate the code beforehand. There's something that's kind of in between. How does Java get to be so fast? JIT. Yes, it has a just-in-time compiler. So it's interpreting the bytecode, but when it notices that a sequence is being executed over and over, it compiles it to x86 code and then executes it. So fundamentally, a JIT engine has to take some data, write to it, and then execute it. So yeah, interpreter is basically right. Fine distinctions in there. So you can't just mandate this for every single program because there are some programs that actually need this functionality, right? But we can at least make it the default on the compiler to compile the code with this non-executable stack, and that way we can make sure that this technique is applied to all possible, the widest array of programs. And if your program needs to disable this, you can, right? Which is how we compiled all of the levels, basically, for this challenge. So how is this actually done? On Linux, there is an NX bit, so the kernel uses this physical address extension, PAE mode, and basically the NX bit executes a region of memory as non-executable. So in this way, it's able to say, hey, this memory region is not executable. There's other names for this technology. So DEP is Microsoft's implementation. So it's data execution prevention, so preventing data from being executed. It actually will support it in hardware. So if the hardware supports this non-execute bit, it will do it. Otherwise, it'll emulate it using software, which would obviously be slower. Kind of the first implementation of this was this write or XOR execute, right? So exclusive OR, you can either write to memory or you can execute memory, but you can never do both at the same time. So this is what this is. So you can see the naming scheme, the nerdier like OpenBSD shows this really nerdy name for this. So basically, you never have memory that's both writable and executable at the same time. But as we just talked about, if you need to write a JIT, fundamentally you need to do this. You need to write out some bytes and then you need to execute those bytes, which actually makes sense now when we talk about, well, this is how a lot of how JavaScript is able to break out of the browser's VM. Because it's actually, literally the JavaScript code is being compiled into x86 code, and then using some exploits, it's able to change control flow of the application to get it to execute in its little code segment. So there's a couple different ways we can do this. So how does this change? So let's assume that the stack is no longer executable. How does our classic buffer overflow attack change? Yeah?
We can't put our shellcode on the stack anymore.
We can't put our shellcode on the stack anymore. Why?
It's not executable.
Not executable. It's going to cause a seg fault. Can we put it in the environment?
No. It's on the stack.
No, it's also on the stack. Can we put it in the heap?
No.
No, we didn't talk about it. It's also going to be not executable. You don't need your heap to be executable. Right? So the question is, what do? Are we dead in the water? Can we not do anything? Yeah.
Overwrite the global offset table with somewhere you might want to go.
But where do we want to go?
C function or libc function.
So the key thing is now we can no longer put our own code into the program. Right? Essentially our shell code, if we try to inject it into the program, anywhere we could write it into the program, It doesn't do anything, right? It can't be executed. So the idea is, but there's actually a lot of functionality that's exposed to the application. So why don't we try to reuse some library function or something? So that's where we get into this. It's called, this is a basic technique called Return-into-libc. So what's a libc function that we might want to target? So let's think about this. What would our shellcode want to do?
Load a shell.
Well, yeah, how do they load a shell?
Run business. Execute.
Run bin sh. What are some of the library commands? Yeah.
System.
There's a system command, right? Which you did in, I've forgotten now. What is that, assignment 1? Assignment 2 seems like forever ago. Assignment 1, right? So the system command is a libc function that you pass it a string, and it executes some program. So what if we're able to call system with the argument /bin/sh? So essentially what we're going to do, we're still going to use a buffer overflow, we're going to overwrite the stack. But now that address that we jump to is going to be the function system, and we're going to set up the stack in such a way that system thinks it was called with the argument /bin/sh. Essentially, we're setting up a fake call frame for system. And any function that's currently linked into the program, we can execute. So this is actually a nice technique if the program itself offers this functionality or has something that we want. We can jump, essentially, remember, by controlling that EIP, we can jump to any function in the program that we want. And controlling the stack, we can pass it any arguments that we want. So we often want system. One thing we can do if there is some section of memory that is executable, we can actually use string copy to copy our shellcode there, which is cool. Yeah.
What areas typically, other than stack, to be executable?
If the program, I honestly don't know. You'd have to look at the segments of memory if that program said it needed some. One thing you can do is you can copy the shellcode, and there's other library functions to change the permissions of that page. So you can say this memory page is now executable, and then you jump to it. So you can do cool stuff like that. But we first need to find the system address in memory. So we can use debugger, we can use proc. So we'll look at this. I believe we'll still use this same simple program, right? So we have our program main. We're copying argv1 onto the buffer foo, and then returning 10. So we've already seen all this. I'm not going to go over this. We can compile it with this, but you will not notice, but I will tell you that there's an option for non-executable stack that's now gone. So if you compare this to the commands that we've used before, you'll see that now we no longer have an executable stack. And you can tell by using this the readelf command to tell you all of the sections. So here it would tell us that, let's see, there we go, that the stack is only readable and writable. So it is not executable. So here, yeah, here you don't have any writable and executable. So here you wouldn't have anywhere to do that. So we've now compiled this program. We have a new binary. The stack is not executable. We can run it. We'll set a breakpoint on main. We'll run it with some foo parameter, and then we'll print out. So remember, when the program loads, right? The program loads, and then the dynamic linker is going to load the libc library into memory. Right? So we can print out what's the address of system using the debugger. And they'll say it's at B7E66310. And I think if we go back, we should see, let's see. No, too far. Aha. Lib, load Linux. I think one of these, I'm not actually used to reading this readelf. No, okay, it's not default. Okay. So if you do info inferior, sorry, that's a little weird here. I didn't properly do the new lines. We can see that we're process ID 14077. So this is telling you, GDB is telling you what the process ID is that's currently being executed. This home Ubuntu a.out. And then, so actually it's a cool thing I found out while I was setting these slides. Inside GDB, if you put the exclamation point before the line, it will execute this as if it was on the shell. So here, this will cat out /proc/14077/maps. So the /proc file system is a file system that we talked about, right? Pretty sure we did. It gives you information about a process. So here the maps shows you the memory mappings, which we'll see. So it says that home Ubuntu a.out is mapped at memory region 0848 to 08049. And it's readable, not writable, but it's executable. And it shows you that this section of home Ubuntu a.out is at 08049 to 08048, and this is only readable, and so on and so forth. So it has all of the sections. And so what's the difference between this and the ELF information?
This is loaded with all the libraries that it formed about.
So this is the actual running process, right? So this is the memory layout of the process. You can do this to inspect any process that's running as well as your user that you have permissions to. And so we can see in here we have the libc.so file, right? So this is where libc is being loaded. And we can see in here that this section is readable and executable, and this should B7E66310 should fall within that range. Yes, I believe it does. And we can actually see there's other stuff. There's the loader that gets loaded somewhere else. So we have all kinds of cool stuff. So we have now the address of system, right? So if we override say PIP with this address, with B7E66310, the start of the printf function will start executing. Or sorry, printf system. But what do we want to pass into? We want to pass in binsh. So how do we get binsh into the program with our shellcode? Yeah.
Put an environment variable or an argument to the program?
So we can put it into an environment variable, we can put it into an argument, but then we'd have to know exactly where that location is in memory, right? And if we're already relying on the fact that system is at this fixed offset, why don't we try to find, actually, so it turns out, I would never have guessed this in a million years, and I still don't know why, but binsh is actually located in libc. So there's the string /bin/sh0 in libc. So this is actually a super cool in GDB command to search for bytes. So you first give it the first offset you want to look for, this B7E26, which is going to be in this segment here, and you'll find that in my case a B7F8684C is the string binsh. Crazy. And this is true for a lot of versions of libc. I still don't know why. I'll look it up at some point. And so we can print out the string at that memory location. It'll tell us, yep, binsh is there. So we actually already have all the ingredients we need. We have system loaded at this location, and we have now the string binsh. So let's call system. So now we're going to run this. So just like before, remember we have 50 bytes of a buffer. So we have 50 bytes of A's. Then we have the save EBP. And now we want to go to the address of system, which was B7E66310. But we want it as the argument to be B7F8684C, right? So this should be the argument to system, right? So that should be the string binsh. Okay, cool. So let's see. So I basically set a breakpoint here on this call. So right before the call, this is what the stack looks like. After the call, we've overwritten our buffer with 50 A's. We've overwritten save EBP with 65646362. We've overwritten the save EIP with the address B7686310. And then we've overwritten above that with B7F8684C. So let's go check, make sure this is right. Let's go over there and over here. Yeah. So B7E6310 is the address of system, and 847 is the string. So 847 and 310. So let's walk through this step by step, right? So we know exactly what's going to happen here. We're going to move 10 into EAX now that we're going to do this so much. I wish I removed that part, but hey, do a little more. So when we leave, we're going to set the stack pointer equal to the base pointer, and then we're going to do a pop EDP. So that's going to change the stack to be up here. It's going to put 65, 64, 63, 62 into EDP. Now we're going to return, which is what we want. And where are we going to return to? The address of system. So system has a bunch of bytes, right? It's going to start executing. It's going to push EBP, and we're just going to go. And if we continue, it's going to tell us that there's a syntax error, there's an end of file and back quote substitution, and then it's going to say that it received a segmentation fault here at B7F8684D. So why? What's the problem here?
Bin slash sh has something that's string.
No, we already looked at the string. It has /bin/sh, then null byte. Or we looked at it in GED, we said x/s, so it's printing it out as if it was a string. Yes?
We can check for the strings up in the stack. Do not dereferences.
No? Yes?
Is it when system returned back to where it was called?
No. We should have seen a shelf first if system was correctly called. So these are all the things I thought of because I did it like this, and I got to this error after making all these slides. And then I had to figure out what went wrong. So put yourself in my shoes. And then I was like, oh, I can keep these and use it as a teaching moment. Yeah?
I'm trying to remember, but don't you need a null after /bin/system and then some arguments that include /bin/system?
Wait, say that again?
Don't you need some arguments that have /bin/sh and then a null and then
That's one we're calling exec.be. Here, system is a function that just takes in a character pointer. Any other thoughts? So we know from here we actually got to the address of system, right? We started executing the system function.
Is there base? No, never mind.
Right? The system will set, I know, I thought base pointer too, but system sets up its own base pointer.
Did we overflow or something and
Did we overflow something? I checked all the memory, no. Yeah.
is there standard in, standard out somewhere we can use?
Nope. Let's think. So put yourself in the system perspective, right? So let's completely get rid of everything below the line, or below the arrow, right? When a function is called, right when system is called, what should be exactly at the stack pointer?
Saved
What was it?
Saved
Saved EIP, because when you call a function, right before you call a function, what does it look like? What's right at the stack pointer? Argument 0, right? Because we're going to push the arguments on from right to left. So argument 0 will be exactly at the stack pointer. Then we say call system. The call function will push the return value onto the stack and saved EIP. So according to system right now, this is the stack as it looks like according to system. What's arg0 to system? BFFF714, exactly. Right? So and what system thinks is the saved EIP is B7F8684C. So this is exactly the problem. So when we look at it here, according to system, this is say VIP, and this is argv0. Right? So we need to, yeah.
Would that be RC or?
What is it actually? I don't know. It's not really important what it is, but it's important that we pass the wrong argument to system. Right? So we got to think. This is where it comes into creating a fake function frame. Right? We want to create a function frame on the stack. We not only want to overwrite the address, the save VIP with the address of system, we want to create the stack that when system starts executing, it thinks it was called with the argument of bin sh. Right? So to get this arg0, we need to have 4 more bytes in between the override of the address of system, then 4 bytes, and then /bin/sh. So that's what we're going to try here. We'll do bcde, and we'll do the address of system, then edcb, and then now the address of bin sh. So that'll finally work. And if we look at y, we'll look at the stack here, and we'll see that after the call, we've overwritten save BDP, we've overwritten the save EIP, and then above that is what system thinks is its save VIP. So actually, like you said, after system is done executing, it's going to go and start trying to execute from 6.2, 6.3, 6.4, 6.5, which shouldn't crash the program, but at that point we've already got a shell, so we don't care when system returns. And then above that is argv0, and if there were any more arguments to system, those would go above that. Yeah, so here when we get to system, we have save VIP and arg0. And using this technique, so this is the Return-To-Libc. So essentially by creating this function frame on the stack, we're able to completely control the arguments that get passed to a function. And not only that, as we just said, when system returns, the next thing that'll start being executed is that 6.2, 6.3, 6.4, 6.5. And so if there was another function we wanted to call, we could put that address there, and that function would be executed after. And so if we do this in a clever way, we can chain multiple functions together. But you need to be very careful with how the stack looks. So using this, completely get around a non-executable stack. So, have we fixed, so does a non-executable does a non-executable stack solve buffer overflows and memory corruption vulnerabilities? No, I hope not, because I just showed you one that worked on this binary. But what did I have to know in order for this attack to be successful? Yeah.
Where system was?
I needed to know where the address of system was and the address of bin sh. Right? So that led to essentially the next evolution in defenses. People said, aha, if you have to guess my memory addresses, well, I'm going to randomize them every time I execute. So ASLR, so address space layout randomization, the short version is ASLR, I'm never going to use the long version again, randomizes the position of the heap, the stack, the program's code, no. Depends on the system. I think on Windows it may, but it also does dynamically linked libraries, so it moves around all of like libc. So every time you run the program, libc will be in a different location. But if you're moving around a library, you need to compile that library so it can be relocatable, right? So that there are no fixed addresses in there. And so not every library will use ASLR. So some libraries will exist at fixed locations, which can be a way around ASLR. So this basically prevents Return-To-Libc incredibly difficult because the library code needs to be guessed. But how can we get around this? Brute force, right? So one question is, depending on the implementation, how much entropy actually is there? right? And so actually on 32-bit, you can pretty much get around ASLR pretty easily. You can do it in 32,000 attempts. You're likely to get it correct. Right, so that's pretty cool, right? So it can still be vulnerable. 64-bit is much more secure. You have an incredible amount. The address space is much larger, so you can move code around significantly. But this is always one of the things you should try to think about, right? If you can't guess it, if you can't break it, just guess, right? You only, as an attacker, fundamentally, you only need to be right once. Whereas the defender needs to make sure you're incorrect every single time. What's another way to break it? What does the whole scheme rely on? Random number generator. So if there was a problem in the way the OS was generating that number, like maybe you're on the same system, if it was using the same source of entropy or a bad source of entropy, let's say it's the random number generator is great.
Having enough memory to randomly move it around enough.
Moving it around, yeah, but let's say it's got all that. How do we define memory corruption vulnerability? What can the attacker do with the memory corruption vulnerability? Overwrite so they can write to memory? What did printf allow us to do? Read from memory. So now, let's say you've randomized everything. Now if I use a printf vulnerability to start reading from the stack, everything on there is a pointer to some place in memory. So with that, and those will be at fixed offsets, right? So no matter where you move it around, it'll be each pointer on the stack will point to some fixed offset. So let's say somewhere at the stack you have a pointer into libc. All I need to do is read that pointer, and now I know exactly where your whole libc is located, and then I can do a really easy return-to-libc attack. So this actually, as ASLR gets more popular, it increases the significance of these, what they call, which I'm blanking on, memory, I'll say dumping, it's all right. Memory leaks. Like leaking memory addresses becomes much more severe. In the previous part, it's not really that severe unless it was sensitive data. But here, literally every single pointer in memory is sensitive, because leaking one of those pointers can tell you where all of the code is located and break ASLR. Okay, ASLR in Linux is enabled by default. There's a setting that you can use to control it based on runtime. So there's stack, library. So this is one thing. So by default, the stack will be randomized and all of the libraries will be randomized. The code will not be randomized by default. So you can disable this while you're testing things. You can't do this on my system, obviously. Change this thing. This is why I actually created the wrapper for levels 5 through 9. So I don't know which one's actually used on, but I think it's 5 and up. Use this wrapper, which disables ASLR just for that program. I was slightly worried about you guys finding there being some 0-day vulnerability and some set UID thing, and then you becoming root. So I figured to make that more difficult, I'd enable ASLR for the whole system, but just disable it for these binaries. So yeah, address leaking, okay. So we think with this, we've solved, right? We've made buffer overflow exploits significantly more difficult. We've made libc significantly more difficult, right? Which makes sense, right? Everything's moving, so how can you possibly jump to some code, right? And this was probably, when was this paper released? can actually generalize this Return-to-Libc approach. So Return-to-Libc started executing at the start of each function, right? And would execute the whole behavior of that function, right? It turns out that oftentimes the binary, the code itself is not randomized at all. It's at a fixed location, just as we saw in most of the health files, right? It's going to execute at a fixed location. So the code of the application itself is not randomized, but that seems like it doesn't help us because the code of the application doesn't call system or call exec.ve with whatever arguments we want, right? But it turns out we can completely generalize this approach and we can use little, what we'll call gadgets that do one thing and then return. So for instance, that will pop EBP and then return. Or that will increment 1 to EAX, as we'll see. So the idea is instead of executing with libc entire functions, let's just find super tiny functionality that we can use that are followed by a return instruction. Oh, 2005, there we go. So actually for a long time, people kind of thought that this problem was solved, essentially. That, hey, buffer overflows were a thing of the past, we're moving on to other vulnerabilities. And then ASLR, when we did ASLR, we did non-executable stack, boom, there's no way around those. And then around 2004, 2005 timeframe is when that started to change. So this paper, if you want to get super into rock, is really good. The geometry of innocent flesh on the bone, Return-into-libc without function calls. Yeah.
Does ASLR have a metadata that we can exploit?
Have metadata? No, I don't believe so. I think the OS is what handles everything, so without breaking the OS, you can't know any of the offsets. And similarly, if the process is running, like we saw the proc file system, if the proc file system is running on, is running as a setuid program, you can't access it. So you wouldn't be able to see the memory mappings of the programs. Okay, so we'll look at this. So let's look back at our fancy dandy, nice libc program, right? Still same code, still same everything. But now we're going to compile it with, actually the only thing on here that we'll talk about later is this F no stack protector. Every one of these has nothing to do with security. So the preferred stack boundary just means there's actually 50 bytes instead of some more stuff here. But what's this static do? What's that static flag? Does that have anything to do with security?
We compile the library statically.
Yeah, so we compile the libraries in statically, so we're no longer using the dynamic libraries. And we can see that it made it a lot bigger. For this simple file is now 716,000 bytes. Right? But, and this actually happens a lot, or you could say we're simulating a very large program with this, what we want to do here. But we've gotten rid of all the other security provisions around here. So, we need to find some gadgets in the binary that will perform some different actions. And what we want to do is essentially encode our shellcode into these little gadgets, right? What did our shellcode want to call? What was that? Call what function? Well, it wants to call BinSH, but how? No, system was the Return-to-Libc. Exec.ve, we want to call exec.ve, which is a syscall. So how do we have to do that? We need to put 11 in EAX. What else? What was it? We need to call int 80 eventually at the end.
Arguments in EBX.
We need to put the /binsh, a pointer to binsh in EBX. A pointer to the binsh, and then null in ECX, and then what in EDX? Either null or a pointer to null, whatever we can do in EDX, then we call int 80. So the idea is we're We're going to find little gadgets. We're going to use them together to accomplish this same thing. And essentially encode our shellcode into these gadgets. So what do we need? Well, like we said, 11 in the EAX, the address of bin sh and edx, the address of an array of the address of / bin sh null and ecx, null and edx. Question is, where can we put bin sh? Now we cannot rely on bin sh to be in a fixed location. So let's say we can write somewhere. Where do we actually put bin sh? Can we write it onto the stack? Let's say we can write to any fixed address. Can we write it onto the stack?
Isn't the stack randomized?
The stack's randomized. We can't write it onto the stack. That's incorrect. So we need to find some other place to put it. So we can use readelf to look at all the locations here, and we can see that there's a lot. But we can see that, hey, the .data segment, right, that holds the writable data of the program is at a fixed memory location, and we know this because we know the code is fixed and it references directly the code that's in .data. So both of these are fixed and don't change with ASLR. And we can see that starting at 08 OE A060 is, what's the size? F20, which is a lot of writable data that we can write to. And we know that this one will be fixed. This memory location is fixed, so if we write the string bin sh there, we're going to be good. So we need to find a gadget. The first thing we need is a write something to an address gadget. So we'll search, and we'll see how to do this later. You can actually choose grep or whatever cool stuff you want to use. We find that in the program at 809 A67D are the bytes move EAX into where? The location pointed to by EDX, right? This is a dereference. So we're moving whatever's in EAX to wherever EDX points to. And then we return. So all we need is these 3 bytes somewhere in executable memory. So this gadget will copy whatever's in EAX into the memory location that EDX points to. So we're going to use this as our first, so this is called a write what where gadget. So as long as we can control EAX and EDX, we can put the string /bin into wherever .data was, and then start executing this gadget, and then we'll write /bin at that memory location. Then we do it again and set up EAX with //sh, and EDX has the next 4 bytes, so .data plus 4, and it will write //sh, then we'll need to write a 0. But we can use this as functionally a write something somewhere. But we need more gadgets. We need to be able to control EAX and EDX. So we can search some more. So we can find that there's a pop EDX gadget. So at 806 E91A, there's pop EDX followed by return. So this gadget will take whatever's in the top of the stack and put it into EDX. How does this help us? Why does this help us? Yeah.
If we control the stack, then we can put whatever we want there.
We control the stack, right? We're fundamentally, we're overwriting the stack, right? We're going to overwrite save EIP, and using that, we can also put data on the stack that will end up in the EDX register. So we can test this out. We'll just test this one gadget. So we're putting the address we want to go to as 0806 E91A. And so what value do you think is going to end up inside EDX when that gadget executes? 10, 20, we'll see. So afterwards, after we do the string copy, the stack looks like this. We have 50 A's, we have 65646362. We have our save EIP that we've overwritten, and then above that we have 62636465. So this is where we're going to execute. So we're going to step through, we move there, we leave, we return, and now we're executing here. So now what's going to happen, what's going to go into EDX? 62636465. Essentially, whatever was right above that gadget on the stack. Right? If we go back to our ROP payload that we generated, we can see here was the address of pop EAX, and whatever was after this got copied into EDX by that gadget. So after this is done, after it pops, then where's it going to start return to? What's it going to execute next? What's the next thing that's going to happen? Segmentation fault. So it's going to try to execute a BFFF F700. Right, so it's going to error out. But here we can see that by putting the value on the stack, right, as part of our exploit, we can, as part of, our stack overwrite, that gadget will copy whatever's above it on the stack and put that into EDX. So, we can use this as a building block. So we have this pop EAX return gadget onto the stack, but we need to not only control EDX, we need to control what else? EAX, we also need to control what? ECX and EDX and oh, we already did D. All of them, A through D, right? All of those registers. So we'll find a pop EAX return at 80db6d6, a pop EBX return at 80481c9, pop ECX, and XOR EAX with EAX. Why is this important? Zero out EAX, right? Which is nice. We could use a pop EAX, but then what would that mean we'd have to have on the stack? We have to have a 0 as part of our ROP payload, right? Which, as we've seen, is problematic, so we want to avoid them whenever we can, right? And then we found an increment EAX return at this location. And we can easily find an int 80. So there's an int 80 at this memory location. This is actually everything we need in order to do, I think, almost any arbitrary computation, but that's essentially what this paper showed, that with enough of these little gadgets, you have a Turing-complete language, and you can create a ROP payload to do anything. And their argument was, hey, as programs get bigger, they'll have more and more gadgets, and there's more things that you can actually do. So we're going to build our ROP payload. So we're going to build our shellcode and encode it as a ROP payload. And it's called usually a ROP chain, because it's a chain thing. I don't know about you, but doing it like this with the little endianness is going to kill me. Right? So you got the little endian, all of those things, and all the data. So let's A, write it in a Python script, so it's nicer. And B, we can actually do it in the correct order. So I'll show you how to do this. So the struct module is your absolute friend when you're doing this. There's a pack function that tells you how to turn an integer and pack it as either little endian or big endian. So that we can use this function and actually have readable, very cool looking, I mean not cool looking, they're just numbers, but numbers that actually make sense based on what we want to do. So we're going to start our payload by creating this object P. And remember, we're trying to conceptualize this. So we first want to copy the bytes /bin to .data. So P is going to be the payload that we're going to generate. We know we first need 50 A's and then a save EBP to get to the save EIP. So what do we have to do next? If our goal is to copy the bytes /bin to .data, what do we need to do? What should be in EDX?
Address of data.
The address of data. which would be an EAX.
/bin.
Yeah, /bin. And then we call that gadget that writes from EAX into EDX. And then we do other stuff. So, we're going to build up our ROP payload. So this is how you use the pack function. I honestly can't remember the first parameter is like a format parameter. It allows you to specify there's different formats. I think it's the angle bracket that tells it little endian, and then the I think tells it that it's a 32-bit. It should be 32-bit, like 4 bytes. So it's going to turn this integer into 4 bytes for us. So this is going to be an 0806E91A. We're going to pop EDX and then return. So this means what needs to be the next value in our ROP payload?
Address of data.
Address of data. Whatever we put next is going into EDX. So we'll put the address of data next. And then we want which gadget? Can we write now?
We need our return address.
We need what?
Where we're going to return to. after
Yeah, what do we want? What
the-
gadget do we want to execute next? Pop EAX. So we want to pop EAX in return, and we want to put the string /bin into EAX. And now we want to go to our write gadget, write what, where. So when this gadget executes, it will move the bytes /bin at the address of .data. So when those 4 execute, we've now copied those bytes there. Are we done? No, we need to copy //sh to at data +4. Why +4? Yeah, we've already put 4 bytes there, right? We don't want to override those bytes, so we want to start at +4, right? And we don't want to include a 0 in our ROP payload, so we don't do /sh null, because that would have to be inside of our string. So now we'll do, and we have to do this for everything, right? So we're going to pop EDX, and the important thing here is that the address is 64, whereas the address here was 60. So this is 4 bytes in front. We're going to pop into EAX //sh, then we're going to call that gadget. And so now we've moved there. So now we have the string at the address of .data /bin//sh. Next, what do we need to do? 0, we need to make sure it's null terminated, right? So we need to copy null bytes at what exact address in relation to .data? .data +8. There we go. So we'll actually get, so this is 068, so this is 8 bytes above .data. Then we're going to XOR, now we go to our XOR gadget. So we're going to XOR EAX, 0 that out. And now we're going to go after that to the gadget of move EAX into EDX. This will move 0 into 080EA068. So now we have 8 bytes of our DAT string, a null terminated string. Are we done? No, we have to still do all the other stuff. We have to set up argv and the environment pointer. So now we know, right? We have the string binsh at a fixed location in memory that will never change throughout executions of this program, no matter what the ASLR status is. So at 080E8060, so we're going to build the argv vector. Where should we put it? What was that? EVP? We don't know what's in EVP. We don't have any gadgets to get EVP. We only have popping into things and copying things. If we had one, maybe we would do that.
Just put it after your binsh and .data.
Yeah, let's put it, so we have 8 bytes of our string, 4 bytes of 0. So starting at data +12 is free. So we can put, but what do we need to put there? Yes, so we need to put the value 08OE A060, and then is that it? What do we have to do after that? We need to put 0 afterwards. We need to make sure we nullify that 0 afterwards. So, same thing, we're going to put 06C, so that data plus 12 into there. We're going to pop 08OE A060 into .data. Sorry, not into .data, into EAX. So this value is going to go into EAX. Then we're going to write out at 08OE A06C, we're going to write the value 08OE A060. Now we can add the null. So we need to do the same thing to add null to data plus 16. If you're really clever, you can move these around. So you could reuse the fact that we were null, that EAX was null at that other right, but you know, when you're doing it by hand, you know, you want to make sure that this stuff is precise. Are we done? What do we need to do next?
Set the environment.
Set up the environment. So for the environment, we actually have two choices. We can actually just use the address of whichever one was null. So there we can clean that out. So then what do we have to do? Yeah.
When you put the address, or you just put that other address at the point? So data plus 12.
Yes. Where does that go?
I guess you could put after the last one.
Ah, no, not quite. That would be a triple pointer. So that would be, yeah.
EBX.
We need to put that in EBX. Yeah, so we need to put that address in EBX. So now we need to set up our call to exec.de. So now we have all the data in memory. Everything's all set up at fixed memory locations. Now we can call exec.de. So remember, we want to call exec.de with the address of .data, the address of .data plus 12, and the address of .data plus 8. So plus 8 is going to point to that 0. So it's going to be an environment pointer that's null, in essence. EBX is the first argument to exec.de. So we need to do a pop EBX gadget, which is going to put 08OE A060 into EBX. ECX is going to be the next one, so we use our pop ECX gadget, and we're going to put the address of data plus C into there. EDX is the third argument, this is the environment pointer, so we're going to put 068, or address of data plus 8. And then EAX needs to be 11, so how are we going to do that? Zero it out, and then do what? Increment it 11 times. You could maybe try to search for a gadget that like moves 11 in there, or moves a higher value and then decrements a few times, but whatever, right? As long as you can just keep doing this as much as you want, right? It'll be 11, as long as there's no restrictions on your input, right? That's one of the things you need to think about. Now we can call int80, and then we're good. We print out our payload. This is going to be our payload to our program. So actually, even though, I mean, it's tedious, right? But it's still roughly on the order of writing your own shellcode, right? It's not super crazy. So now we can run this. Very important thing you'll notice, or maybe somebody who has really good memory, what's the difference that I did besides changing the program that's being executed between this and the other ones?
The quotes.
Double quotes. Why do you think I needed that?
Because that has to be the input.
Yeah, because the shellcode, or not the shellcode, because this payload has white space characters, like a horizontal tab in it, and so if you do it without double quotes, it'll work, but it'll pass multiple arguments and completely mess things up. That took me like a half hour to figure out what was wrong. So I get stuck on these things too. Don't worry. I presented to you like this is just how it is, but you know, I struggle with this stuff too. So double quotes are super important and super necessary here. Literally, this example will not work, but we're going to want to set our breakpoint at a location right before the leave. So you can see we've overridden the stack. I'm right before the leave, so I'm not even showing any of the other parts of the stack. Right? We've already done our overflow, and we're going to walk through this very quickly. So we're going to return. So now we're going to start executing from our gadget. So these are all the different gadgets in memory, right? They obviously are not next to each other. I literally ran out of space to separate them, and it is too much of a pain. So we're gonna pop EDX, we're gonna put 08OEA060 in there. We're gonna return to a gadget that pops EAX. We're gonna put this value into EAX. So this now is /bin. We are then going to copy that value at this memory address, 060. And if you're wondering, yes, it was just as tedious for me to make these slides as it is for you to watch them. But I think it's important to actually understand the flow of what's going on here and how the relation is between that code that we created and like what's actually going on here. So now we're going to write out, this would be //sh, so we can actually see, maybe we're starting to decode the X, 2F is slash, so this is //sh. We're going to move that there. Then we're going to pop the next value at 68, and we're going to XOR EAX, so we're going to 0 that out. Now we're going to move 0 at address of data +8. Then we're going to return, and now we're going to pop that into EDX, and we still have like a ton more to go. It's actually not that large if you think about it. It's like 40 steps, but you know, for arbitrary computation with this, it's pretty cool. So now we return here, pop EAX. Now we are moving, right, so this is the important part, right? This is where we're setting up the argv vector. We're copying 08OEA060 to 6C, right? So we're setting up our stack correctly. Popping there, XORing EAX, now we're zeroing that out, so we just here moved 0 to 070, which is 16 bytes plus data. And now we got all of our fun stuff, so now we pop EDX, so now we're setting up EDX, we return, we're popping ECX, and we return, and now we pop EDX, so now 3 of our registers, EBX, ECX, EDX, are all set up with the values that we want. EBX points to the string bin.sh, ECX points to a pointer, points to a memory location, and at that memory location is the address of the string bin.sh, followed by a 0, and finally the environment pointer just points to a null pointer. Now we're XORing EAX, then we have 11 increment instructions, which, trust me, we'll get it up to 11. We get up to here on the stack. We then return from there to int 80. We call this, and we finally get a shell. So we can actually see that before we execute this shell at this int 80, we can see that at this memory location is the string /bin//sh. Right? It's important that we know that it's null terminated because GDB is checking for that when it prints out the string. We can look at 08OEA06C, we can look for 2 values, and we'll see that at this memory location, because this is argv pointer, we can see that there is a pointer to this. There's the memory address of bin.sh, followed by null. At this is 0. We can continue, and we will actually execute a new program. So we've essentially done execve with this string, this argument vector, and this null environment. Actually, technically, I guess it's array contain or an empty array or whatever. So this is a ROP payload for this program that is fully ASLR proof. It doesn't matter how much ASLR you apply to this program. We will be able to execute any arbitrary computation and any arbitrary commands from here. There's an important point. You may think that we could skip this argv and make it null, but that was an optional step. And I'll tell you, we were doing a capture the flag competition, I think it was DEFCON Quals, and I'd been working on this program for like 3 or 4 hours, and I got to the point where I was doing the ROP payload, and it was working on, of course, on my machine, like you're used to in GDB, and then I'd run it on their system and it wouldn't work, and I was literally pulling my hair out for, I think it took me then another 2 hours to realize I was passing null as the second argument, which would work. It would be no argument vectors, but on that particular operating system, if bin.sh was executed with no argv parameters, it would terminate. And so when I changed it to be something like this, that took more work, it actually worked. So this is why I'm presenting it to you like this. Don't let it do it another way. Questions on this? Yeah.
Is there a reason .data isn't controlled by ASLR? Why it doesn't actually randomize data?
Yeah, I believe it's because the code segment's not randomized, and the code segment has to, is using the .data segment as global variable. So any global variable you have will be located in the .data segment, so when you need to reference it in the code, you need to reference the full address. Yeah?
What if your target binary is sort of too simple, doesn't have all these gadgets?
That's probably not worth targeting, is the short version. You may be able to do something with the gadgets that are there, right? So it would take you looking at the gadgets by hand and trying to figure it out. So, to lift your spirits, there are automated tools to find gadgets, so you don't actually have to do it by hand. To be completely honest, that's how I made this example. I ran this tool on it, it outputted the gadgets. So there's I would say Pwn tools. So if you want to look into a library to do this stuff competitively, Pwn tools is a fantastic library that has all kinds of cool payload generation, ROP gadget finding tools, all kinds of super cool stuff. Almost all of the top CTF teams use Pwn tools to write their exploits. ROP gadget is the tool that I use, which is really good for finding gadgets. So it will show you all the gadgets in a program so you can look to see what's useful. They also, definitely ROP gadget has it, I think Pwn tools may have it too, is they will automatically build the ROP chain for you. So they will analyze all the gadgets, try to find a right what, where gadget, and then try to find the right pops and stuff and create the whole thing for you automatically. So it's super cool. So, is this it? Are we done? Should we just give up? Time to go home? We can't possibly stop these memory corruption attacks. The attackers are just too smart. What made this attack possible?
Access to data.
Part of it, yeah.
Your input is as long as you want it.
My input could be as long as I want to do what? Why did I need my input to be really long?
Oh, to have all the pops and use all the tools. It took a
Yeah,
while.
but what was the first domino of that whole chain?
A buffer overflow.
To what? Overflowing what?
Save the IP.
Saved EIP. Still fundamentally I have to overflow saved EIP. So an idea is, hey, let's try to prevent overflowing saved EIP. So one way is canaries. So canaries were an older technique. The idea was, hey, let's put something on the stack before saved EIP, and then we'll check it before the function returns and make sure that that canary value is still there. If it's not, we terminate. So stack guard is a way to do that. There's all kinds of different canaries. And the idea is the compiler changes the epilogue so that every time a return instruction is performed, it checks the canary and makes sure that the canary is valid. So it needs to be recompiled, so it doesn't work on old code. And it introduces overhead, which means some people don't actually use them. So F stack protector and F no stack protector, these are the ones that enable or disable canaries on Linux. So now we may think game over, right? There's no possible way we can do this, except what we can do is, well, there's two things. Let's see. No, that's fine. If we can guess the canary, we can overwrite the correct value, right? Fundamentally. We can still sometimes maybe overwrite the function frame. So if the canary only protects EIP and not save EDP, then we can overwrite save EDP, and as we saw, we can use that to shift the stack and control everything. And we may think game over again. Of course, some very smart people came up with this approach called BROP, which stands for Blind Return-Oriented Programming, which works against a target server, so let's say like a web server that has a buffer overflow, has canaries. Essentially the idea is when you do an overflow, you're only changing that last byte of the canary value. So if you can change that last byte of the canary value, and the other thing I should say, canary values don't change between different requests to the program. So usually canary value is randomly determined on startup, and then that value is used. So the idea is if I'm able to write onto the stack, and I can overwrite the last canary value, I can try 0 to 255, and one of those will work, the rest of them will crash the program. And so then I brute force one byte of the canary. And then I can do it again with another 255 and get the second byte, the third byte, the fourth byte. That way I can break the canary, and this paper and these tools actually show you how from there you can do a completely blind ROP attack and figure out gadgets like in a completely blind manner, which require a lot of requests but still actually work. So this should terrify you. Nothing is safe. Except for control flow integrity. So the idea here, I'm trying to get through this so we can start with that on Wednesday. Control flow integrity, the central idea here is, the problem is in all these attacks, I can make the program go and execute something that it shouldn't, right? There was never a call from the return of my function to the start of system, for instance, right? That control flow, if you think about all the paths through the program, there's only a fixed number of control flows. So it's actually a super old idea from 2005 that says, hey, every time there's a return or a start of a function, check where you're going or where you came from to make sure that it was actually intended by the programmer. So control flow integrity, essentially it turns out that even if you have perfect control flow integrity, there's enough of dynamic stuff that can go on. There's a paper called control flow breaking, I believe, or control flow bending, where even by going through the program graph in the exact right control flow order, you can cause arbitrary computation to happen and have basically the same as a ROP attack. So everything's horrible. Just so that you've never taken a security class but learned about Metasploit, Metasploit is a tool that has a lot of known attacks for known systems. So you can download this, you can actually run and shoot exploits at various systems. It's free, it's kind of cool. And Kali Linux, it still is Kali, right? Did they change the name at some point? Maybe no? It still is, right? Okay, cool. So this is a Linux distribution that's actually very cool that you can install and play with. That has all these security tools pre-installed. It has Metasploit. It has literally any kind of scanning, all of the Wireshark, the packet capture tools that we talked about. Okay. So, in conclusion, you should be terrified. Nothing works. Everything is vulnerable, right? You can exploit applications through providing unexpected inputs, generating unexpected environmental conditions. You must sanitize user input, right? As a developer, it's on you to be aware of what are the potential security problems with your system. So the idea is you should think safety, right? So you can't code securely 100% of the time. Literally no one person can and no team can. So you need to think about safe ways of coding, safe languages, trying to use existing protection mechanisms to try to mitigate risk as much as you can. Even if you do all that, so to completely turn it around, you still have problems with the application's logic, right? So still, like we said, even if you still have a coupon system that allows you to use a coupon and keep using it enough times to reduce the price to free, that's still a vulnerability in your application, right? It's not a memory corruption vulnerability, it's a problem with your application's logic. So this is your job as a security analyst, is to understand and look at each program adversarially, right? That's why the homework you're doing now is so important, because you're looking at each level and thinking, how can I break this, right? Using every possible way you can. This is what you have to do when you're looking at an application, right? How can I break this? How can I make it do what it's not supposed to do? All right, nice.
Is this the last homework assignment, and then the final thing?
Oh, I asked that at the beginning. Fill in your